Welcome to all. So here we are going to see constitution of alloys in engineering materials and metallurgy. So first, what is meant by alloy? Alloy is the mixture of two or more metals in a solid solution in which the major portion is called metal. So in this diagram, iron combined with the carbon to form a steel. So why we go for alloying in material science? So the pure metal always have the low strength and high ductility. So it is not practically impossible to use them in industrial applications. So that's why we are going for alloying. So alloying is mainly increase the material strength and hardness, toughness, corrosion resistance, ductility and malleability. First, we are going to see the solid solution. So what is my solid solution? So it describes the family of materials which have range of compositions and a single crystal lattice. So next we go for types of solid solution. So there are two types of solid solutions. One is substitutional solid solution and another one is interstitial solid solution. In substitution solid solution, classified into two categories. One is disordered substitutional solid solution, ordered substitutional solid solution. So first we see the substitutional solid solution. Here the solute atom substitute the solvent atom in a crystal lattice structure. So in this diagram, the solute atom replaces the solvent atom in any order. So that is called substitutional solid solution. So in that, classified into two categories. One is disordered solid solution, another one is ordered substitutional solid solution. So in the diagram, we see the zinc atom replaces the copper atom in a random order. So here the solute atoms do not follow any specific order, but the atoms are distributed randomly in the lattice structure. So another one is ordered substitutional solid solution. Here the zinc atom replaces a copper atom in some sequence. So some uniformity followed during the substitutional sector. So here the solid solution is heated to its recrystallization temperature and then cooled very slowly. So the atoms are rearranged due to the diffusion that takes place during cooling. So this result uniformity and defined ordering of the atoms in a lattice structure. So that is ordered substitutional solid solution. So then the next type is interstitial solid solution. Here the solvent atom and the solute atom are there. So interstitial atom is placed between the solvent atom and the solution atom. So here no substitution takes place in that interstitial solid solution. The solute atom fit into the space between solvent or parent atom. So these spaces or voids are called interstices. So next we are going for phase diagram. So mainly phase diagram, we know the cooling curve. The solidification of molten metal is plotted in a graphical form. In x-axis the time is marked and y-axis the temperature is marked. So here the types of cooling curve. So broadly classified into three categories. The first curve is cooling curve for pure metal. So here the P to Q region is called liquid and Q to R is a liquid to solid transformation takes place, and R to S is completely solid. So here the time is increased, so temperature gradually decreased of the each cooling curve. The second category is cooling curve for binary solution. So here the liquid plus solid region Q to R. So here the two phases are present to form a binary solution. The third one is cooling curve for a eutectic system. So here both liquid and solid and rapid cooling takes place. So the liquid phases are present and liquid plus solid phases are present and completely solid phases are present during this curve. So next we go for iron carbon equilibrium diagram. So it is a very much useful in understanding the microstructure and the properties of cast iron and carbon steel. So it is a graphical representation of time versus and temperature and also the various percentage of carbon. The phase diagram is constructed by plotting the carbon weight percentage along the x-axis and temperature in y-axis in terms of degree Celsius. So before we going for iron carbon equilibrium diagram, we should know the what is allotropy. So allotropy refers to the possibility of existence of two or more different crystals for a substance depending upon temperature. So this phenomenon is called polymorphism. So in the iron carbon equilibrium diagram, the allotropic temperatures are very much important. So first we mark the temperatures in the iron carbon equilibrium diagram. So first initially the iron is in alpha ferrite state. So 0 degree to 910, the completely the iron forms a body centered cubic structure. So the state of iron is called alpha iron. So after that 910 degree Celsius to 1395 degree Celsius, the crystal structure is face centered cubic. The gamma ion is present in that region, so it is also called austenite. So then the third allotropic stage, the temperature of 1395 degrees Celsius to 1539 degrees Celsius, the crystal structure is body centered cubic. In that region completely delta ion are present. So after increasing the temperature of 1539, the solid is converted into the liquid state. So first these are the very important of allotropic temperatures in iron carbon equilibrium diagram. So next we mark the temperature of branches. So first one is 723 degrees Celsius. We mark the temperature in iron carbon diagram. Next 1147 degrees Celsius and 1492 degrees Celsius. So we must remember the temperatures clearly. So first initially we mark the temperatures in y-axis, then we go for percentage of carbon in x-axis. The carbon percentage varying starts from 0% to up to 6.67% of carbon. In that the carbon percentage of 0 to 2% is called steel. The iron with the carbon percentage of 2% to 6.67% of carbon is called cast irons. So in that steels we classify into two category. One is hypoeutectoid steel, another one is hypereutectoid steel, and cast iron is hypoeutectic cast iron and hypereutectic cast iron. So after marking the percentage of carbon, so we draw the iron carbon equilibrium diagram in step by step. So initially the curve takes place at the 0 degree temperature. So then it goes into the 723 degrees Celsius and we touch the 910 degrees Celsius. In that region completely alpha ferrite takes place. So after that you mark the curve in 910 degrees Celsius to 0.8% of carbon. Then you connect with the 1147 degrees Celsius temperature line and you connect the curve into the 0.15% of carbon to the 1395 degrees Celsius temperature. So in that region completely gamma ion takes place. It is also called austenite. So further the curve is continued start from 13952 connect with 1492 degrees Celsius temperature line and closes with 1539 degree Celsius. So these are all the curves we plot the in iron carbon diagram. The carbon percentage of 0.8 percentage in the carbon percentage. The eutectoid reaction takes place. In that eutectoid reaction, one solid that is called austenite is transformed into two different solids. So one is ferrite and cementite. So it forms the during cooling the solid is transformed into two separate solids. In that 0.8 percentage of carbon at a temperature of 7 to 3 degrees Celsius, in that reaction is called eutectoid reaction. The another reaction takes place at 4.33 percentage of carbon at temperature of 1147 degrees Celsius. In that region, the liquid is transformed into two separate solids during cooling. So we increase the heating, we increase temperature, two different solids converted into the liquid state. So in that the two separate solids is austenite and cementite. The another and this reaction name is eutectic reaction. So in that the another reaction takes place at 1492 degrees Celsius, that is called peritectic reaction. In that region, during cooling, a liquid plus delta ferrite of one solid, liquid plus solid is transformed into new solid during cooling. So the new solid is called austenite. So in that reaction names peritectic reaction. So these are the very important reactions in iron carbon diagram. Then you mark the different phases in the iron carbon diagram. So in that alpha ferrite, perlite and cementite and ledubrite, austenite and liquid plus delta ion. So these are the different phases present in the iron carbon equilibrium diagram. The reaction is very important for this iron carbon diagram: eutectoid reaction, eutectic reaction and peritectic reaction. Thank you.